Hello everyone, my name is Matthew from Group 2, and today we're going to present about the effect of pH and radiation towards microbial growth. So what are the effects of pH and radiation towards microbial growth? In terms of pH, the optimal growth pH is the pH most preferred for growth by an organism. The minimum growth pH is the lowest pH value for an organism, and by the optimum pH, they are classified into acidophiles, neutrophiles, and alkaliphiles. The next is the effect of radiation toward microbial growth, and it will be explained by my friend Nicholas.
So here, I'm gonna explain about the radiation. So, what is the effect of radiation toward the microbial growth? Radiation, like UV lights, will damage the DNA strands, which can affect the capability of microbes to multiply. Other radiations, like gamma rays and X-rays, will have the same effect towards the microbial growth.
Has been previously mentioned before, the effects of the pH and radiation toward microbial growth. In order to utilize these effects on controlling this microbial growth is by using this one of the four equipment that we can use in our daily lives. So the first is using a chemical, using a carbonic acid to lower the pH and propionic acid to increase the pH. This reason why is because every bacteria has different capability of living, whether they can live in high pH or low pH. So to counter that, we can use these chemicals. The second is ionizing radiation. Third is UV box sterilization. This can sterilize large items, especially from groceries. You can use this sterilization box to kill all the microbial growth that exists on that item. So the fourth is gamma rays.
What is the optimum pH and radiation for microbial growth? Most bacteria prefer neutral pH 6.5 until 7.5. For example, mold and yeast grow in wider pH range but prefer pH between 5 and 6. Acidity inhibits most microbial growth and is used frequently for food preservation, for example, pickling. Alkalinity inhibits microbial growth but not commonly used for food preservation. Acidic products of bacterial metabolism interfere with growth. Buffers can be used to stabilize pH. As mentioned at number 1, radiation inhibits microbial growth instead. Organisms can be classified as acidophiles or acid-loving that grows at a very low pH of 0.1 to 5.4. There are also neutrophiles that grows in pH 5.4 to 8.5, and alkaliphiles or alkali-loving that grow in alkaline or high pH 7 to 12 or higher. For example, soil bacterium agrobacterium grows at pH 12.
Next is the classification of microorganisms based on pH. So first we have acidophile. These bacteria can grow best at acidic pH. The cytoplasm of these bacteria are acidic in nature. Some acidophiles are thermophilic in nature. Such bacteria are called thermoacidophiles. The example of acidophiles are microscopic algae such as Cyanidium caldearium and Dunaliella acidophila. The microscopic fungi such as Acondium silatium, Cephalosporium, and Trichosporium cerebriae. Sulfolobus, Microphilus, Ferroplasma, Acondium, Diobacillus dioxidans, Diobacillus sphaeroxidans, and Thermoplasma. These microbes are found in a variety of environments, including geysers and sulfuric pools, as well as in the human stomach. Next is neutrophile. This kind of organism have optimum growth in acidity-neutral environments. It also includes most species of microalgae and other organisms that form phytoplankton as well as some soil-dwelling bacteria and yeast. Escherichia, Euglena, and Immoparmesion are the example of bacteria in the neutrophiles. And the last is alkaliphile. Those bacteria grow best at alkaline pH The example of alkali files are Bacillus, Alkalophilus, Natronobacterium, and Vibrio cholerae, which the optimum pH is 8.2. These microorganisms thrive in alkaline lakes, soils, and other high pH environments. In slike dams of Lake Calumet, Southeast Chicago, the water can reach a pH of 12.8, which is similar to caustic soda. Some bacteria related to the Clostridium and Bacillus live in that extremely alkaline environment. Mono Lake in California and Octopus Spring and Yellowstone Park are examples of environments where alkaliphilic microorganisms are found. But if microorganisms grow best at pH 10 or higher, it is categorized as extreme alkaliphiles. These alkaliphiles have stable enzyme and the cells can be used for biotechnological and other applications with high pH.
So now we move to the classification of microorganisms based on those two parameters. There are two types of radiations. First is ionizing radiation. In the form of very short wavelength and high energy, atoms lose electrons or ionized. The major forms of ionizing radiation are X-rays, which are artificially produced, and gamma rays, which are emitted during radioisotope decay. Low levels of ionizing radiation reproduce mutations and result in death, whereas higher levels are directly lethal by direct damage to cellular macromolecules or through the production of oxygen-free radicals. Second is UV radiation. UV radiation kills organisms due to short wavelength and high energy. Classification based on radiation is categorized as extreme movements. Survivor doses of ionizing radiations are Deinococcus radiodurans and bacterial endospores. Resistant under ionizing radiations are Deinococcus bonsiensis, Pulmonoensis, Sibariensis, Coopereensis, Gradis, and Mysiensis. Produce the UV-absorbing compounds under UV stress, Stenotrophomonas maltophilia, Exigobacterium, and Staphylococcus sp. Marine Cyanobacterium, UV hyperresistant, Prochlorococcus medford. Isolated from ambient lakes and are UV resistant are Exigobacterium sp, Acinetobacter sp, Bacillus sp, Micrococcus sp, and last, Smingomonas sp. Isolated from spacecraft is Bacillus hornecii. A novel species, the Greek red pigmented strain found to be UV resistant, is Hymenobacterium. Resistant to UVR is Streptomyces culbisporus. Last but not least is UV radiation. Gram-positive strain is Mycobacterium maritipicum.
Hi, so now we're gonna talk about how can pH inhibit microbial growth. So as we know, environment with pH below 7 are considered as acidic, and pH above 7 are considered as basic, and at 7 are neutral. So pH affects the structure of all macromolecules. So what is optimum growth? Optimum growth pH is the most favorable pH for the growth of an organism. Lowest pH value that an organism can tolerate is called the minimum growth pH, and the highest pH is the maximum growth pH. So these values can cover a wide range, which is important for the preservation of food and to microorganism survival in the stomach. For example, the optimum growth pH of Salmonella is 7 till 7.5, but the minimum growth pH is closer to 4.2. So there's a 3 classification of microorganisms based on the pH parameter. So the first one is acidophils, grow optimally at pH less than 5.55, and the second is alkaliphils, grow best at pH between 8 and 10.5, and the last is neutrophils, grow optimally at a pH within 1 or 2 pH units of the neutral pH of 7. So the most bacteria are neutrophils. So change in pH modify the ionization of amino acid functional groups and disrupt hydrogen bonding, which in turn promotes change in the folding of the molecule, promoting denaturation and destroying activity. So to conclude, pH can inhibit microbial growth if the organism were not in their optimum growth pH. So, for example, extreme acidophiles and alkaliphiles grow slowly or not at all near neutral pH.
So, how can radiation inhibit microbial growth? Radiation techniques in inhibiting microbial growth can be divided into two, namely ionizing radiation and non-ionizing radiation. The first one is ionizing radiation, such as X-rays and gamma rays. It is ionized water and other molecule to form radicals, which is a molecular fragment with unpaired electrons that can disrupt DNA molecules and proteins, and induce double-strand breaks in DNA molecules. This could directly cause DNA mutation to occur, or mutation can be added as a cell tries to repair DNA damage. As this mutation builds up, they eventually contribute to cell death. The second part is non-ionizing radiation, such as UV radiation. It allows the neighboring thymine bases on the same DNA strand to covalently bind together and creating what is called thymine-thymine dimers. When DNA polymerase meets a thymine dimer, it does not often add sufficient complementary nucleotides or two adenines, and this leads to mutation that can eventually destroy microorganisms. Okay, so this is the reference that our group used for this presentation. Thank you for listening.